Hey folks, welcome back. In this video we're going to look at travelling waves, so let's get into it. It starts here by saying that a transverse wave can be defined mathematically by the travelling wave equation. Note that the following derivation is not examinable, but you should be able to recognise the mathematical form for a travelling wave and be able to use it in calculations. So let's go through the derivation here of the travelling wave equation and see if you can understand the steps as we go. So firstly it says consider the wave shown below. So we have a y-axis and an x-axis and we've got this cosine wave shown. And it shows a particle here moving up and down and says the particle moves with simple harmonic motion. It then says the value of the displacement y is dependent on the x value and also on the time t. A particle of the medium through which the wave is travelling will not move in the x direction, but will move with simple harmonic motion in the y direction. So we've just seen that with this particle in the picture here. It then says a sine or cosine function is the simplest mathematical form of a wave. And in this example, it doesn't start at the origin, it starts at maximum amplitude away from the equilibrium position. So that means this is a cosine wave here. It then says that since the particle undergoes simple harmonic motion, we can apply initial conditions just like we did in the simple harmonic motion topic. And remember, initial conditions just means what happens when time t equals 0. So we can say that if y equals 0 at time t equals 0, that is, we have 0 displacement at time t equals 0, then we would use y equals a sine omega t. However, if the displacement y equals the maximum amplitude a at time t equals 0, then we would use y equals a cos omega t. So we would use cosine instead of sine. And again, this was seen in the SHM topic. It then goes on to say, now consider the wave below moving from left to right. Now we've got these 2 points P and Q, and we can see that they're positioned one whole wavelength apart, which is labelled the distance x here. And it says that when time t equals 0 and a equals 0, the position of the particle P is given by y equals a sine omega t. And we've just seen that from the initial conditions. Now consider point Q, which will have begun its motion sometime t before P. So if Q is over here and the wave is moving from left to right, then it means that point Q in the wave was once where point P was, but at some time t in the past. So we can say the time between the particles will be given by this expression here, time equals distance over speed, where the distance here is given by x, the one wavelength distance there, and the speed v is the wave speed. So that's just from a speed distance time. And therefore the equation for point Q is given by this expression here. So it looks a wee bit more complicated than just our y equals a sine omega t, which describes point P. So we can say that y equals a sine omega times t minus x over v, where that is just the time difference between particles Q and P. And lastly, it says since omega equals 2 pi f and v equals f lambda, this can be written as y equals a sine 2 pi times ft minus x over lambda. So all we're doing there is substituting in for the omega here to get 2 pi f, and then if we take the f inside the brackets to get ft minus fx over v, then we've got the ft part shown there, and instead of fx over v, we can rewrite f over v is equal to 1 over the wavelength, 1 over lambda. So that's why we get this minus x over lambda part here. And this gives us our travelling wave equation. So remember, you don't need to be able to explain the steps that we've just done to derive this, but it helps to understand it. So we've got y equals a sine 2 pi times ft minus x over lambda, where y is the displacement of the wave measured in meters, a is the amplitude of the wave measured in meters, f is the frequency of the wave measured in hertz, t is the time at which the particle is observed, measured in seconds, x is the distance of the particle from the origin of the wave measured in meters, and lambda is the wavelength of the wave measured in meters as well. Lastly, it says to note that the equation above with the negative sign in the brackets is for a wave travelling from left to right. So this negative sign means it's travelling from left to right. However, if the wave is travelling from right to left in the opposite direction, we simply replace the negative sign with a positive sign so that the equation becomes y equals a sine 2 pi times ft plus x over lambda. So you need to remember that for a wave going from left to right, it's going to have the negative sign in the brackets, whereas if the wave is travelling from right to left, it's going to have the positive sign in the brackets. That's all for this video, folks. Thanks for watching. If you made it to the end, I really appreciate it. Make sure to give the video one of these, subscribe to the channel, and I'll see you in the next one. Take care.